by the way, I'm going to be talking about a methodology now that assists managers in making decisions about what type of tester to build. Ordinarily, a test engineer wouldn't necessarily make this distinction, but I'm making it now, and it would be good if test engineers knew more about these sorts of things. So like factors are, how much experience have you had with building similar testers? Like if this is the 6th modification of a product, probably you're going to use almost the same tester to test the next level up one, especially if it's the same platform. And then there's the final estimated cost of the UUT. If it's very small, you can't spend much testing each unit, or you're going to have to go to statistical techniques. And there's a volume level of the nominal build. That's how many you're building at a time in batches. And of course, there's the skill level of the operator. There's funds available for the tester project. And then there's a volume level of the estimated life cycle build, funds, which means that you want to try and estimate at the beginning how many of these things you're going to make over its entire life. Because remember, life cycle is really critical now in product manufacturing. And so basically, this provides the funds to feed back to R&D for the tester. So that if a manager is going to make a decision, the question is, if there's a large number of these going to be made over a long lifetime, then of course it's worth more investing in higher level testing. Then there's the cost to build the tester and write the software or the test procedures. That's another factor, which very often in testing, that cost exceeds virtually almost all the other costs today. Just programming the thing to work properly. Then there's the likelihood of field failure, of course, and the cost of supporting field failure. And so what I'm going to do now, I'm going to give an example. I'm going to go out of my my talk here. So what I've developed here is a methodology which you learn in places like business school to help make decisions. Now they don't make decisions. This is a messy thing for engineers. They do not understand the concept. But you know, if you're going to decide to do something a particular way, some managers, just from their experience, say, we'll do it this way or that way. But a method that could enhance that, it doesn't make the decision for you, but it enhances the possibility of making a decision, is to take these factors like I mentioned and put them into some sort of a sheet, an Excel spreadsheet, which I've developed for this particular one, and which you say, well, how valuable, how important, I should probably say valuable, how important is this factor on a scale of 1 to 5? And what this allows you to do is it allows you to rank the factors. See? And then you say, well, if I make a mistake, what's the impact of that error over here? And then what you do is you multiply this number times this number to get a number over here. And in the end, you end up with a bunch of estimates, if you will, of how important that particular factor is. But what you're interested in is the accumulation of all of these. And so what I do here is I do this all as a bunch of fancy math on an Excel spreadsheet, but I say that the calculated value, the computed value is 0.44, which is a normalized value, where 1 is definitely you should be using an auto tester. Mid value is 0.36. It says semi-automatic likely, but maybe trending towards some more automation. And then if it's 004, it means they all have 1s. Well, that doesn't make any sense if they're all 1s, but nonetheless, that would be the bottom of the circumstance.